Welcome to Techdaily.ai, and thanks for joining us for another deep dive.
Great to be here.
Today, we're really going to get into something fundamental to almost all the AI you use every day, but maybe don't always think about. AI inference.
That's right. It's kind of the engine running behind the curtain.
Exactly. Like when your smart assistant just gets what you're saying, or you see those amazing AI images popping up online, that's inference at work. So our goal today is to demystify it a bit, show you how it connects to the tools you're already using, and hopefully give you a couple of those aha moments.
Yeah, connect the dots, so to speak.
Precisely. And we've got our expert here to guide us through the deeper stuff.
Happy to help break it down.
Okay, but before we really dive in, just a quick word about our sponsor.
Sure.
This deep dive is brought to you by Stonefly. They're a trusted solution provider and advisor, covering everything from enterprise storage, backup disaster recovery, hyperconverged setups, VMware, Hyper-V, Proxmox clusters.
Right, the whole virtualization stack.
Yeah, plus AI servers, which is obviously relevant today, SA365, that's their turnkey security appliance, and public and private cloud solutions too.
Pretty comprehensive.
Definitely. So if you're looking at infrastructure, check them out at stonefly.com.
Good to know.
All right, let's get into it. Inference. In normal life, if I say inference, I probably mean like figuring something out based on clues, right? Like dark clouds, wind picks up. I infer it's going to rain.
A logical conclusion based on evidence.
Exactly. So when we talk about AI inference, is it basically the same idea? Or is there more to it in the tech context? What are we really talking about?
That's a great starting point, and honestly, your everyday understanding isn't actually that far off. It captures the spirit. In AI, inference is specifically the process where the system takes a Model 1 that's already been trained on a whole lot of data.
Right. The learning part is done.
Exactly. The learning's done. And it uses that trained model to generate some kind of output based on that learned knowledge. It's the application phase. It's taking all that complex pattern recognition from training and, actually using it to do something useful.
Okay, so it's not just knowing, it's doing.
Yeah.
Applying the knowledge. I remember seeing this simple analogy, peanut butter and grip.
Ah, yes. A classic.
Most people instantly say jelly, right? It's like this automatic pattern completion we do.
Yeah.
How does that relate to AI inference? Is AI just doing that, but like way more complicated?
It's actually a surprisingly good analogy because it gets to the core idea, pattern matching. Our brains learn associations over time. Peanut butter goes with jelly.
Right.
AI models, after seeing, millions or billions of examples of text or images or whatever,
Massive amounts of data.
immense amounts, they learn these incredibly complex statistical patterns. So when you give it peanut butter and, it's not thinking, oh, sandwiches, it's calculating, based on all the text it's seen, what word has the highest probability of coming next.
So it's statistical prediction.
Fundamentally, yes. It infers the most likely completion based on the patterns it absorbed during training. It's predicting what you want or what fits the pattern. And yeah, it goes way beyond just simple phrases. It applies to recognizing objects, understanding sentence meaning, generating realistic audio, all based on recognizing and completing incredibly complex patterns.
Got it. It's applying the learned patterns.
Yeah.
And I think you mentioned earlier, it's how we use a trained model to do something useful. Can you unpack that useful part a bit more? What's inside that trained model that inference actually puts to work?
Sure. So a trained model isn't just one thing. Think of it having a few key parts. First, you've got the model parameters. These are basically millions, sometimes billions, of numbers, weights, and biases in a neural network, for instance, that the model learned during training. They kind of encode its knowledge.
The learned stuff.
Exactly. Then there's the model architecture. That's the structure, the blueprint of the AI, like how the different layers and nodes are connected. A model for images, like a CNN, has a different structure than one for language, like a transformer.
Okay. Structure and knowledge. What else?
And then there's the configuration. This is sort of the instructions for the job, how to handle the input, what kind of output is expected, maybe some specific code for the task it needs to perform right now. So inference is the active process. It takes those learned parameters, runs them through that specific architecture according to the configuration for the task at hand, using new data it hasn't seen before.
Right. Training builds the brain. Inference uses it.
You got it. Training is the heavy lifting upfront. Inference is the faster, real-time application of that learning.
Okay, that makes the distinction super clear. So which AI models really depend on this inference process? Is it mainly the new, flashy generative AI stuff we keep hearing about, or is it broader than that?
Oh, it's definitely broader, though generative AI is where it's really getting attention now. But yeah, deep learning models heavily rely on inference. That includes the large language models, the LLMs, behind things like ChatGPT or Gemini.
The ones that write text.
Right. And the models that generate images, like Midjourney or DALL-E. Also, audio models that create speech or music. Their whole purpose is basically to predict and generate based on learned patterns, and that prediction is inference.
Okay, so language, images, audio. What about things like recommendation engines? When Netflix suggests a movie or Amazon suggests a product, is that inference too?
Absolutely. Recommendation systems are a prime example, and they've been using inference for ages, way before generative AI became the big thing.
Really? Ages.
Well, in AI terms, think about most advertising models online or the algorithm that decides what YouTube video to show you next. They're constantly running inference. They look at your past behavior, clicks, views, purchases, mix it with data from millions of others, and infer what you're most likely to want next.
So they're predicting my next click or watch.
Pretty much. And these are often called, traditional or classical AI models. They're not usually generating brand new content like an LLM, but they are making sophisticated predictions based on learned data. So, key point. Inference isn't new. It's been fundamental to AI for a long time.
That's a really important clarification. It's not just this new generative trick. Okay, so beyond prediction and recommendation, I heard inference is also key for classification, like telling things apart.
Exactly. Classification is another core capability powered by inference. It's about the model assigning a label or a category to something. Think about training again. You might show a model millions of images, painstakingly labeled cat, dog, car, tree, whatever.
Right, label data.
Through seeing all those examples, the model learns the distinct features, the shapes, textures, common backgrounds associated with each label. It builds an internal concept, statistically speaking, of what makes a cat a cat. Then, during inference, you show it a new picture it's never seen before. The model analyzes the patterns in that new image, compares them to the patterns it learned for all the categories, and infers the most likely label. This looks most like the cat patterns I've learned.
So it's not just predicting the next word, it's inferring what is this thing?
Precisely. Recognizing and categorizing based on learned distinctions.
Which I guess brings us straight to the famous cat example.
Yeah.
The AI identifying a cat in the picture. That blew a lot of minds when it first started happening reliably. How does inference make that possible?
Oh, yeah, that was a huge milestone. The amazing part wasn't just that it could identify a cat, but how it learned. Nobody explicitly programmed rules like pointy ears plus whiskers is cat.
Right, it wasn't a checklist.
Not at all. It learned by seeing massive amounts of image data. Through inference on that data during training, it essentially figured out for itself the complex combination of visual features that signify cat. It built its own representation of catness. So when you give it a new photo, the inference engine kicks in. It processes the pixels, extracts features using its learned internal layers, compares those features to the cat pattern it developed, and infers, yes, probability of cat, 98%. And maybe even draws a box around it. It shows how inference allows AI to understand and interpret the world from raw data.
It's pretty incredible when you think about it learning that way. So if inference itself isn't new, but the results are getting so much better, are we just doing the same inference process, but maybe with bigger models or faster computers? Is it just getting better in that sense?
That's a really good way to put it. The fundamental process is still inference, apply a learned model to new data. But what's changed dramatically is, well, two main things. The sheer scale and sophistication of the models themselves.
Bigger, more complex brain.
Yeah, exactly. And secondly, the massive increase in computational power available, especially specialized chips like GPUs and TPUs. So the models can learn much deeper, more subtle patterns from vastly more data, and we have the horsepower to actually run these huge models efficiently during inference. It's the same concept, but supercharged.
You can really see that with AI images. A few years back, they were interesting, but often weird. Hands with 6 fingers, things melting.
Oh yeah, the uncanny valley was strong. Lots of artifacts, weird physics.
Totally. Now, sometimes you genuinely can't tell if an image is AI or real. How much is that leap down to better inference?
A huge amount of it is. Those older models, they might have learned local patterns, like fingers are long and thin, but they struggled with the bigger picture, the semantic consistency.
Yeah.
They didn't really grasp the underlying structure of a hand or how light works on skin realistically.
Right. They knew the pieces, but not how they fit together.
Exactly. Today's models, especially things like diffusion models, trained on way more data and using clever architectures like transformers with attention mechanisms, have a much deeper, more holistic understanding. When they infer how to generate a hand, they're considering the anatomy, the pose, the lighting, the context all at once. That deeper understanding, applied during inference, leads to vastly more realistic and coherent results.
And that leap isn't just visual, language translation. I mean, wow. I remember using those early online tools. You could kind of get the gist.
Kind of, but it was often very literal, clunky, definitely not smooth or conversational.
No way. But now, generative AI translation is often so good people use it for like customer service emails or professional documents without thinking twice. That's a massive change.
It really is night and day. And again, it's about the evolution of inference. Those older systems were mostly statistical machine translation. They worked by matching phrases based on frequency in huge bilingual texts. This French phrase usually translates to this English phrase.
Sort of like a giant phrasebook lookup.
Kind of, yeah. It lacked deep grammatical understanding or context. Generative AI, using neural machine translation, works differently. Models like transformers infer the meaning of the whole sentence or even paragraph and generate a translation that sounds natural in the target language, considering grammar, idioms, and flow.
Because they understand the relationships between words better.
Exactly. Things like the attention mechanism let them weigh the importance of different words across the sentence. So the inference process isn't just swapping phrases, it's understanding and reconstructing the meaning fluently.
Okay, so the quality is clearly leaping forward. Which makes me wonder, can we actually measure how good inference is getting? Is it just looks better, sounds better, or are there actual numbers?
Oh, absolutely. It's rigorously measured. We don't just rely on gut feeling. We quantify inference performance based on how well the model does its specific job. For classification, we measure accuracy, precision, recall how many cats did it correctly identify, how many things decalled cats actually were cats, and so on.
Right, specific metric.
For language, there are benchmarks like BLEU scores for translation quality or perplexity for how well a model predicts the next word. For images, you might use things like FID scores to compare the statistical distribution of generated images to real ones. So yes, lots of quantitative ways to track progress.
And is this measurement just something you do at the very end, like grading a final exam? Or is inference used during the training process too, to help improve the model as it learns?
That's a critical point. Inference is deeply integrated into the training loop itself. It's not just a final check. While a model is training, which can take days or weeks,
A long time for big models.
a very long time, developers are constantly running inference tasks on the current version of the model using separate validation datasets. They check its performance against those metrics we just talked about.
Like little progress checks along the way?
Exactly. This feedback loop is crucial. If the model isn't performing well on certain tasks, or if its accuracy plateaus, they can see that in real time through inference, and then adjust the training parameters, maybe feed it different data, or even tweak the model's architecture. So training and inference work hand in hand iteratively to improve quality.
That makes sense. So we're seeing the benchmarks go up, the technical scores improve,
Yeah.
but also, just as users, we feel it's getting better, right? Someone from Google, Niranjan Hira, made that point beyond the numbers, have we noticed?
And the answer seems to be a pretty clear yes. Right. I mean, think about it. Translation is smoother. AI images are more stunning and believable. Search results often give you that summarized answer right at the top now, which is super helpful. The way we interact with these tools feels less clunky, more intuitive.
Yeah, definitely less friction.
Right. That improved user experience, that feeling of, wow, this actually works really well now, is the direct result of all those underlying improvements in inference quality and capability. People have definitely noticed.
Okay, let's make it even more real. Can you point to a specific example, maybe in a Google product many of us use, where this improved inference is really flexing its muscles right now?
A great everyday example is AI overviews in Google Search. When you type in a query now, especially a complex one, it's not just finding web pages with those keywords anymore.
It feels different.
It is different. Your query actually goes to multiple specialized AI models. Inference kicks in big time here. Different models work to understand the intent behind your words, what you're really asking. They infer the best way to find the answer, pull information from various sources, synthesize it, check it, and then generate that concise summary you often see at the top.
So that little paragraph isn't just copied from one website.
No, not at all. It's a newly generated piece of text created through multiple inference steps designed to directly answer your query based on information gathered from across the web. It's inference orchestrating a really complex information retrieval and synthesis task almost instantly.
That's pretty amazing. And you also mentioned something earlier called agentic work,
Oh.
where AI doesn't just give you info, but can do things for you. How does that extend inference?
Right. Agentic work is kind of the next evolution. Think of traditional inference as the AI telling you something, translating text, identifying a cat, summarizing search results. The AI is an information source.
Okay.
Agentic work uses inference to figure out a sequence of actions needed to achieve a goal you give it, and then actually perform those actions. It's inferring a plan, not just an answer.
So, like, instead of telling me how to book a flight,
It might actually book the flight for you. You would need
Yes,
to infer the steps, search airlines, compare prices based on your criteria, select seats, maybe even fill in your details and handle payment, interacting with different websites or systems along the way. It's using inference to understand the goal, break it down, execute steps, and potentially even handle problems if something goes wrong.
wow, okay, that's a big step up. Moving from providing information to taking action.
Exactly. It's an extension of inference into the realm of autonomous task execution. It requires even more sophisticated inference about planning, reasoning, and interacting with the digital world. That's where a lot of research and development is heading.
So inference is getting smarter, more capable of complex tasks, even agentic ones. What are the other big trends shaping its future? What's driving the changes right now?
One of the absolute biggest drivers, maybe the biggest, is the push for cost reduction and efficiency. Making inference cheaper and less power hungry is critical.
Why is that so important?
Well, think about deploying these powerful AI models globally. If running inference for every single user search query or translation request is incredibly expensive or uses tons of energy, it's just not sustainable or scalable. To make AI truly accessible and useful for everyone, everywhere, you have to bring down the cost per inference.
Right, it needs to be affordable to run at massive scale.
Precisely. So a huge amount of effort goes into making inference more efficient, getting the same or better results, using fewer computational resources.
Can you give an example? Like, how would you make a big model like Gemini cheaper to run?
Sure. So the goal isn't just to make elite version that's less capable. It's often about keeping the core intelligence, what we call the model semantics, its main task, but changing the computation paradigm, essentially optimizing the underlying math and code.
How do you do that without losing quality?
There are several techniques. One is quantization, where you reduce the precision of the numbers the model uses. Instead of using highly precise 32-bit numbers, maybe you use 16-bit or even 8-bit numbers. This makes calculations much faster and uses less memory, often with minimal impact on accuracy for inference tasks.
Okay, using less precise numbers, what else?
There's also pruning, where you carefully remove connections or neurons in the network that aren't contributing much, and model distillation, where you train a smaller, more efficient student model to mimic the outputs of a larger teacher model. Also, designing models to be sparse, meaning only a fraction of their parameters are active for any given inference. All these aim for the same quality with less work.
So, lots of clever software tricks to slim down the workload. Is it all software, or does hardware play a role in this efficiency drive?
Oh, hardware is absolutely crucial. It's a constant interplay between hardware and software. That's why you see companies like Google investing heavily in custom chips like our tensor processing units or TPUs. The upcoming 7th generation, codenamed Ironwood, is specifically designed with an inference-first philosophy.
Inference first. What does that mean in practice?
It means the chip architecture is optimized specifically for the types of calculations that dominate inference workloads. Things like massive matrix multiplications, which are core to neural networks, are heavily accelerated. It also means more memory bandwidth to feed the processing units faster and built-in support for those lower precision number formats we talked about, like FP16, bfloat16, or intit, which run much faster and use less power.
So the chip itself is built to do inference calculations really, really fast and efficiently.
Exactly. But hardware alone isn't enough. You need the software to take advantage of it. That means better compilers that translate the AI model code into super optimized instructions for that specific hardware, and improved frameworks the software libraries developers use that make it easier to build and deploy these efficient models. It's the whole stack working together.
Hardware and software optimized hand in hand. So if you boil it all down, all this work on better models, smarter techniques like quantization, faster hardware like TPUs. What's the ultimate goal here? What's the big picture aim for AI inference?
The big picture, the ultimate goal, is really about delivering better quality AI, more accurate, more helpful, more capable, but doing it with a much smaller computational footprint and therefore at a significantly lower cost.
Better, faster, cheaper, essentially.
Pretty much. But the why is important. It's not just about saving money, it's about making advanced AI accessible and practical for billions of people. Lower cost and higher efficiency mean you can embed powerful AI into more devices, more services, more applications, reaching more users and solving more problems. It's about democratizing AI, making it a truly helpful tool for everyone, everywhere.
What a journey through inference.
Yeah.
We started with that basic idea of drawing conclusions and ended up here. We've seen it's this core pattern matching engine, not new, but constantly improving. It powers recommendations, classification, like spotting cats.
Uh-huh.
And we've seen that incredible evolution from, clunky translation to fluent conversation, from weird images to photorealism. And now this huge focus on making it efficient, affordable, accessible through things like specialized hardware and software tricks.
It's a really dynamic field right now.
Absolutely. Which leaves us with a fascinating thought, right? As inference keeps getting better and cheaper, what kinds of things that seem like science fiction today might AI be able to do for us soon? How could that change how we interact with tech every single day? Definitely something to keep an eye on.
For sure, the possibilities are expanding rapidly.
Well, this has been incredibly illuminating. Thanks so much for breaking that all down.
My pleasure. It was a great conversation.
And as we wrap up, a final thank you to our sponsor, Stonefly. Don't forget to check out their special offer, a 100 terabyte immutable and air-gap SSO NAS that's network-attached storage with single sign-on for just $8,995. A really robust solution for data security and management.
Sound like a solid deal for that capacity and security.
It does indeed.
Yeah.
So thank you again for tuning into this deep dive. Keep exploring, keep asking questions. We'll see you next time.